Thanks, Jim. Hey, everybody. I'm Steve McGhee. We may have spoken before. I've kind of worked with some Sabre folks and even some Lowe's folks, so I recognize a few names here. I am not in Southlake. I'm actually in California. So I'm in San Luis Obispo, California, and I am an SRE, and I live in a town called SLO. And if you think that's funny, you are halfway on your way through this talk. So congratulations. I'm going to talk about some reliability stuff and some SRE stuff, and it's going to be pretty theoretical. It's mostly about the theory part, and then there will be some practice. I promise there will be some actual things that you can take away. I think Jim suggested that there's like half an hour, 45 minutes-ish time. I don't know if there's that much slidage, so we may get into questions before then, and that's always fun. But we'll see what we got. Okay, so that's me in black and white. I'm on all the socials using my name. I have a sneaky H in my last name, which allows me to always get that spelling, which is great. And I work at Google. I should say, backing up, I should say the full bio is that I'm a reliability advocate, which is part of DevRel. And I think I made up the title reliability advocate. I don't think it's real, so that's cool. And I used to be an SRE, so I was an SRE for about 15 years. At one point, I left Google. I went to a enterprise that was moving from on-prem data centers onto the cloud, and my job was to get them there. And we did. We tried to get sort of SRE practices along the way, and it turned out it was super, super hard. So I learned a lot, not only about how customers adapt and adopt to cloud, but also just how far today's sort of operations work, especially in sort of like entrenched enterprises, is from what I had known in. Let's get into it a little bit. So there's going to be a bit of like blah, blah Google slide where we'll go kind of quick through that. See, look at that shiny pictures about multicolored data centers. So you're probably all familiar with Google. It's big, has a lot of computers. The idea here is just to kind of show that, we're big and we have a lot of computers. No, the idea is that we have a highly scalable system, right? So you can handle billions of concurrent customers. It's pretty awesome. You've probably seen this before. This is all of our points of presence as well as our data centers. Again, with the bigness, the network is interesting. That's the typical. This is what we do. What does this have to do with reliability? It does mean that we have more control over where Google or where customers sort of land. We have to rely less on like the unwashed internet and can handle more of the traffic management ourselves. So if you've ever seen the concept of in GCP, the concept of a premium network tier versus a standard network tier, the default is the premium one. It's kind of funny. You can choose to take the standard network tier, which is the sort of the above picture. I don't recommend it. I recommend the premium one. Okay, so this is the more interesting bit. Now we're getting into stuff that didn't come from the marketing department. So there's three main parts of any cloud, right? Of any like computer, right? Computer system, and that's compute, storage, and networking. So what is special about Google? Like, do we just have a bunch of computers? Then you just like plug into them and you attach disks, and it's just like you could do it in in your basement, just the same. Not really. The difference is software. So all of our large systems are governed by software, obviously, because we're a software company. So the first one is Borg. So you've heard of Borg. If you've heard of Kubernetes and heard the whole story, the thing that came before Kubernetes is called Borg. It's still definitely running. It is a very large part of what makes Google work. I would say it is the thing that makes Google work. It is, behind all 8 of our billion user products and everything else as well. This is a funny picture that shows, doesn't matter. So it's an arbitrary bit of architecture. Borg is big. Borg works very well. It's very compliant. It moves everywhere you want it to move and more. It's great. It is all made in software. It is all proprietary. There's no way for us to export it. So we made Kubernetes instead. In storage, and all these diagrams are in the public domain, so I won't get in trouble for this. And you can find the papers that these are based on. So in storage, we have a system called Colossus. Colossus is not a SAN. It is sort of a SAN, right? Like you can think of it as a SAN, but it is, different. So it has all these concepts of, has these control planes and it has, D servers that are just holding bytes, and everything is replicated and has all these. It's very fancy. So the point of this is it's extremely scalable. A case in point, I used to work on the YouTube uploading and processing system, which was the thing that you upload videos for YouTube. And about 9 years ago when I worked on it, the amount of data that was uploaded every day was about 35 years of video per day, which is a lot of bytes. And that number is definitely bigger now. And then finally, networking. We don't just have, plugs and stuff. We have software-defined networking, and, it's really fancy and great. The system that we use for that is called Andromeda. If you've ever been down the halls of overlay networking, this is what this is. So the idea is that, every customer has their own, private network that's built on top of our real network. So we have these virtual networks. This is where VPCs come from. And every time you make a change to your system, that network needs to, be updated. So it has to change very fast, and it has to allow a lot of throughput. So again, lots of software doing a lot of things for a lot of customers. Very special. So what's so great about it with regards to reliability? Borg has some pretty cool things. I'll just highlight the one is live migration, if you've heard of that before. I used to be on the SRE team that worked on this as well, so I'm extremely familiar with it. It is the coolest. The way that it shuts down, or it transfers over like sort of the soul of your machine to a new computer before scheduled maintenance occurs, and it brings it back up again, and you basically don't notice that it went down. It's pretty awesome. You probably heard the stories about like the Heartbleed bug and things like this, where we were able to mitigate the entire fleet without anybody noticing. So that is pretty great. Colossus, it has other great features. Some of them that are important are the fact that every bit is at least triply replicated. You can't get less than that. And we have what we call distributed metadata model. So if you want to know like where your file is, it's not in one, the thing that tells you which computer your file is on is also spread across many computers. And so it's very hard for the availability of that, data structure to go down or be corrupted or anything like that. So it's very cool. And finally, the kind of most important, or one of the more important parts about Andromeda's resiliency is the idea that it fails static. So if Andromeda's control plane or control systems fail in any way, the networks that it controlled don't just stop working. You just can't program them anymore. They just kind of stay where they were. Generally, that's totally fine or good enough. So this is a common pattern that we use across many systems, Andromeda just being one of the bigger ones. So, okay, moving on. If you haven't already seen this type of thing, this is worth knowing about. So you've probably already heard of zones and regions. This is just pointing out that we have something internally called clusters inside of those. These are Borg clusters. The reason why I tell you this is not just to talk about clusters or anything. It's just to say that zones and regions are the building blocks that you should think about when it comes to failure domains. So services are tied to a zone or tied to a region. There are some that are multi-region, or sometimes we call them global. Those are pretty rare now, which is good. Because it turns out there's only one global, and it's called Earth. So if that one goes down, you're in trouble. But if you have something that you want to stay up and be resilient to a failure domain problem, you should have it be in more than one things. So either more than one region or more than one zone. So that's kind of the point of this, is to show you it's a nested model of failure domains. And obviously, if you lose a region, you lose all the zones and clusters inside of it. But if you lose one cluster inside of a zone, you don't lose all the rest, right? So being aware of this topology is pretty important when it comes to understanding the consequences of which product you choose and how you expect it to run. Okay, here's another view of basically the same thing. So we have services that live in these failure domains. So at the top, you can see we have some services like load balancing and cloud storage that might be either global or multi-regional. Like I said, there's only one of these, right? There's, global load balancers. So I'm only referring to global layer 7 load balancing. There's only like one failure domain there, so we treat it very carefully. I'm papering over a lot of, kind of fancy things that we also do under the covers, but you can't have like, two completely independent sets of global load balancers because they have the word global in them. On the other hand, you can have, regional GKE clusters. These are great. They have a better uptime than zonal GKE clusters. But if you break one by yourself, like if you push a bad config or you accidentally, kubectl delete or whatever, like it'll go down. It'll tell you, it'll do exactly what you tell it to do. So having multiples of these is important. And if you want to be really resilient to regional failures, which are things like tornadoes and fires and floods, you want to put them in separate regions. This seems obvious when you're looking at a diagram like this, but when you go to actually architect your system, you find there's a lot of trade-offs involved. You kind of have to understand like why should we do this, and like what's the cost and what's the value of having our compute across multiple regions, multiple zones. Essentially, it comes down to resilience. Maybe it's redundancy. Maybe it's reliability. All these R words that are all slightly familiar and similar to each other. The way to think about it is that services that live in a zone, for example, like VMs, they live in one zone. They generally are 99.9% available. And you have to kind of look at the SLAs. They change a little bit. So like single VMs are actually, I think, 99.5, but other services are around 3 nines. So if you think of that as 40 minutes of downtime per month, that's kind of the ballpark. And then regional services tend to be what we call 4 nines, 99.99% available. So that's given the 40-minute number again, but we're going to say 40 minutes per year this time. So that's close enough to kind of keep it in your head. And the important thing to think about here, when I talk about 40 minutes per month and 40 minutes per year, I want you to take that really seriously, and I want you to not think of it as a worst case scenario or a best case scenario. Like, it is a guarantee. That is what you're gonna get. So the sort of joke that we use internally is like, if you have all these 9s, you might as well take them for a while, or take them for a spin once in a while. So if we haven't used up our error budget in these services, we're going to do something that allows us to use that up. So my point is, like, even if we don't have like a hurricane or something like that, the point of this 0.1% of error is that so we can do maintenance essentially. So it's really tricky as a human to look at 99.99% and not say that's pretty much 100, right? Like, it's not. When it comes to computers, that little bit, that 0.01%, is actually a pretty big difference especially when it comes to 24/7 services. So do yourself a favor and don't round up. That's my suggestion. Okay. While we're at it, this is Ben. Ben is one of the founders, or maybe the founder of SRE. And he likes to say that 100% is the wrong target, which is totally true. This is important. Again, like 99.99% is not the same as 100%, and you shouldn't really be aiming for 100%. Come on, nice and slow. Okay. Here's kind of the top, these are like the 5 pillars of SRE. If you haven't seen these before, this is essentially how the books are broken apart. You can see there's definitely an overlap with DevOps. I believe these are actually the 5 pillars of DevOps, and then we're sort of we're matching SRE practices to those pillars. We won't go into that too far. This is another kind of view on kind of what SREs do all day. This is like the areas of practice, like as opposed to the pillars or the principles. This is kind of the activities that SREs do. Okay, let's get into the more fun stuff. So this is funny. Like, why do we have these shaped things? One thing that I found in speaking with customers a lot is that often we'll find customers will say things like, why can't you just keep your VMs running all the time? Like, that's not that hard. We do it all the time. Like, we have this data center, the VMs stay up all the time, and your silly cloud keeps turning them off every once in a while. Like, why can't you hit 100% just like us? And the reason is because we're not trying to hit 100%. We're trying to hit 99.95%. And we do that on purpose. So the way that I try to explain this is, the traditional model is the one on the left, right? It's component level reliability, where you have a really solid base. You have a very large room, and you make it very cold, and you have a bunch of redundant power in it, and you never you never turn it off, and everything, whatever's running in there will always run in there. Think of a mainframe, right? Like mainframes under, meters and meters of concrete are pretty secure, and they tend to not break, which is great. But when you have a really secure bedrock like that, you sort of tend to rely on it to always be up, and then you don't build resilience into your software. And what happens then is that you actually tend to lose reliability as you build more complexity on top. So as you add more and more software on top of the thing, the system becomes less resilient and less reliable. So that obviously is not great. So what do we do instead? At Google, we kind of flip it around. So we say, let's just assume that the components at the bottom of the stack will fail all the time. So Google's kind of got stories about, like, zip tying disks to racks, and using Legos to hold things up, and all kinds of silly things, because we kind of just didn't take the hardware very seriously. And that was on purpose. That wasn't just because like we're weirdos. The point was we wanted to make the hardware fail, kind of like make that normal. Expect the hardware to fail. And instead we want to make the software more resilient as it got up the stack. So our infrastructure software and our application software on top of that always expects the layer below it to fail. So this is a very different model of programming, right? And different model of how you're architecting your system and how you're operating your system. The benefit of this also, not just in terms of failure, is this allows for hyperscale data centers. So this allows us to have scaling out, right? Or it allows us to do horizontal scaling as well, because we're able to add more and more and more machines, and we don't have to take the whole system down. We can kind of hot add capacity. We're adding small bits at a time, and the software above us on the stack is taking advantage of that. So there's a lot to talk about in these silly little purple pictures. The most important thing out of this, though, is if you think of the pyramids on the right, you're building something that is more reliable on top of something that is less reliable. So if you have VMs that are only up 99.5% of the time, how can you build a system, a service, that is available 99.99% of the time, or 99.999% of the time? It turns out you can. There's this whole process around it. The best way to think about it, though, is think about RAID. So the disks in your computer or in servers or things like that, they fail all the time. We know this. Like, disks aren't great, but SANs and like network attached systems kind of are up all the time. How does this work? And it turns out, software and redundancy allows us to have like this kind of new idea of a more highly reliable system built on top of less reliable parts. And that's the way you should think about it, right? Build your software like the way you would build RAID. Allow a disk to fail, and you don't have to worry about it, right? So it used to be that, if a disk failed, freak out, right? Go run to the data center and swap it out. But with RAID, we don't care, right? When a disk fails, what's our budget? Let's wait for 10 of them to fail. Then we'll send someone over and replace all 10 at the same time. Okay. More theory. This is obviously coming from another slide deck. I tend to kind of change colors here because I pull these from different slide decks. Okay, so let's talk about risk. When we have services that make money, or products that sort of make us money, what we don't want to happen is to not make that money. That's kind of the goal, right? We want to keep the system running. And you can substitute money in for, whatever it is that you're actually achieving with your system. But money is sort of like the economist way of thinking about virtue, right? Bad things that can happen. You can have outages, right? I'd like to think of there's two kinds of outages. There's planned maintenance, right? Like what's going to happen. And there's unplanned. Like the most obvious ones that we like to think about are natural disasters, because we don't get to, we don't have to blame ourselves for those ones. They just happen, and we kind of go, oh, that's a bummer. But there's also stuff that we did cause. Oops. So we can have bad pushes, right? So we can push bad data, bad binaries, bad configs. We can do all kinds of messed up stuff. We can accidentally, hit the wrong key. We've been there. We know that. And that is essentially an unplanned outage. Other things that can happen that aren't quite outages are poor performance. So like these are just kind of degradation. Like stuff slowed down. That's no good. People don't like that. The inability to innovate. If your system is so hard to change that you can't actually push code very fast, that is a risk to the business. So that's kind of a more subtle one. And of course, there's security as well. If you can't update all your machines with patches, you're going to be in trouble. So first thing, we're going to do some fake math here. Our first formula is going to be that risk itself is impact times probability. What does that mean? Well, if you look at the link below, and we can send these notes out later, there's a talk at SRECon from a guy named Matt Brown. It's a great talk. You should definitely check it out. The idea is, what is the impact of this thing happening if I push the wrong button or push the the wrong config? What happens? Does the whole system fail, or just part of it? Or like, how much money do we lose per second? Stuff like that. Well, what are the odds of that thing happening? So if we can get those two numbers, we can get a quantifiable risk score. So impact can be any of these measures. I like to think of dollars per second, but it can be like brand reputation as well. So how do we figure out the probability? We can use all kinds of ways of thinking about this. The talk, if you go check it out, kind of boils down that a lot of these are really hard to kind of really believe in or to really measure even. But if we get down to bad minutes per year, we can have a single number. So essentially, like, what are the odds that this will happen, and what is the outcome of this thing happening? So, if we lose a disk, and it takes an hour to replace it, and we don't have RAID, then it's going to be an hour of full downtime. But if we do have RAID and we lose a disk, it's going to be 0. So we have like a single way of measuring reliability gains. Okay, the next thing is, let's measure impact a little bit more carefully. It's blast radius times time. So how long does the outage take, and how big is that outage? So your blast radius could be a few different things. It could be everybody, right? The whole system is down. That's not great. You can go all the way down to the point where you're only affecting, some very small percentage of your customers, which is way better. So if 0.01% of your users notice that you are down, then are you really down? Questionable. So think of this outage over time as area under a curve, and you're going to kind of integrate that area. So you're going to get, the impact is going to be the amount of outage times the amount of time. And you can measure these with traditional models like MTTR, MTTD. Try not to confuse like cleanup events or like, when it was alerted versus when it actually took effect. So we have these 3 numbers. The idea here is we want to reduce any or all 3 of these numbers: the probability, the blast radius, or the time. So how do we do that? There are so many ways we can do that. And so here's just a sample set of them. And in parentheses, you can see what it is that they're reducing. For example, if we added multi-cluster deployments, like pushing things to multiple clusters, we're changing the blast radius at hand. So we're reducing the blast radius of any change to that cluster. If we're doing canary releases, same thing, blast radius. We can add exponential retries with jitter. That reduces the probability of a network blip, essentially, to take things out, because during the network blip, anything that was trying to make a call across the wire that broke will not just fail, it will just kind of hang out for a second, and it will try again later, right? So you're kind of trading off time for reliability. You're getting more reliability, but you're losing a bit of time. And maybe that's acceptable. Depends on what you're doing. Okay, so we're almost done, actually, surprisingly. So this is, so I have a hard time writing the word reliability, so I write R9Y instead. And just to be confusing, I call it Ronnie, but that's neither here nor there. Okay, so we have this thing we call the Ronnie map, and I'll show it in a second. But the idea is, like, there's a lot of things you could do. This page right here. So these are some things you could do as a reliability team. But like, there's more than that. There's a ton of stuff you could be doing, right? And these are all like capabilities you could build into your platform, or that your team could develop, or like a tool you could buy, or there's a million things out there that you could be working on. And some of them are kind of have prerequisites, and some of them are more important to work on earlier, and some are more like advanced. So what do you work on first? We've developed a map to help you figure that out. So the idea is we want to be able to help you figure out where you are today, what you're already capable of doing, and where you want to get to. Like, just how reliable do you want to make your systems? We can help you then sort of plot a route, if you will, across this map. a journey, right? And the intent is to get this to a point where it's sort of self-service, where you can look at it and you can say like, oh yeah, we are here, we want to get there, we should buy these items, we should build these things, and we should adopt these cultures. So here's a kind of a snapshot of the map itself. If you're at Sabre and you've been working with Brian Wong and all, we've shown a bunch of this with him and a few of his teams, something about inventory. I'm not really sure what the names of the services all are. So you may have seen this already inside of Sabre and elsewhere. This is all public. It's a work in progress. If you go to r9y.dev, you can check it out yourself. I don't think I have a link on here yet, but you can see it. And the idea here is really just to gain feedback and hear what people think about it. But you're free to check it out. But we're going to move on past that a little bit more into something that's a little bit more manageable right now. So if you're interested in adopting some capabilities, some reliability stuff, and you don't want to like deal with this whole map thing, you just like, Steve, just tell me where to start. Like, what should I work on, regardless of where we are today? Here's my suggestion. So this is how I think you should start. First up, define some SLOs and understand how you can derive an error budget from that. So this is per service, per critical user journey, if you can figure that out. But get some SLOs in place and understand how your customers depend on your service. The next thing is introduce incident response program. There's a lot of this documented. There's PagerDuty has a really good set of articles on how to do this well. Essentially, you want to go from a chaotic management of incidents to like a managed version of managing incidents. So you want to have a process, and like people should write these things down and use the same terminology and all that stuff. The beauty of this is that then you have a structure in place where you're going to start developing like shared knowledge, right? And so we call these postmortems. So the next step is develop blameless postmortems. And even more importantly, have a postmortem review process within your company. So this means you are not bringing it to like managers to approve. Think of it as like you're bringing your postmortem to a peer or to like an upperclassman even, someone who has seen a few of these and can kind of give you advice on your final draft. So you want to be able to write down like what happened, what we did wrong, what went well, what we could do next time. After this is you're going to have a bunch of things you could work on, right? After you have a bunch of postmortems, you have a bunch of work that comes out of those. So how do you prioritize that work? There's a prioritization matrix that is also linked in this document that I can show you guys. Essentially, it gives you a reliability backlog. So you should have software engineers who are dedicated to burning down backlogs. That's kind of how we do things these days. Assign some of them to the reliability backlog, and you're off to the races. Pretty soon, you'll start to see impact reduction. So your outages will be less painful. And you can, if you're in really good shape, you can adjust your SLOs to be tighter and better. Okay. Yeah, there's a few points here. If you can't do SLOs today, it's a hard place to start because you can't even do them. So why would you not be able to do SLOs? If you don't have the accuracy in your observability system to be able to do SLOs, it's going to be tricky. So making sure that you can actually understand what it is that your system is doing under the covers is kind of a prerequisite for doing SLOs. So really kind of the 0th step here is improving your observability to the point where you can actually build out SLOs. Okay, this is kind of annoying. Don't worry about this. Finally, this is the most confusing diagram I've ever drawn, but it says a lot. So the idea here is you want to be able to build what we call a platform. So I think it was Kelsey Hightower said Kubernetes is a platform for platforms. I think that's pretty good. The idea is that you want to be able to build out a system for getting your code into production, right? And that's going to be done by introducing capabilities into a platform. So you can have this big platform full of capabilities and not have any code in it at all. No customer-facing services whatsoever. At some point, you're going to have to start adopting services. So a really not great idea is to take the most important service at your company and put it on the brand new platform and be like, let's go. We don't even know how this thing works yet. I have seen this many times and it's not a good idea. Doesn't work. So that's what that red line implies. Like, don't put the high risk, high value service on the platform right away before you've gotten all the capabilities in there. or that you gained any confidence in how those capabilities work. Instead, add some low-risk services in, just some little toy stuff up front that, if it goes down, it's not a big deal. You want to get those in place so that you can start to build out the capabilities over time. So what's an example of a capability? Just basic CI/CD stuff is the first place you start. Can you push code into a cluster? Can you build on that over time? Can you, add, sanity checks to your deployment so that you can validate that the service is running well before you, update the load balancer. That's a separate capability that you've added to your brand new platform. Okay, I think that might be the last slide. So this is an example of a filled out reliability map. So you could print out the map and you can just go with a red pen and check an X and question mark. And, that's the process you would follow. Okay, I'm done talking, and my throat is reminding me that I should be drinking water.
Yes, take a chance to take a sip, Steve. Thanks for running through what you had. I'm just lining up my windows here so I can see you and the chat and everything at the same time. So if you have questions for Steve on any of the topics that he's had, please put them in the chat. You can put them in the Q&A chat, the general chat. I will fill in sometimes with my own questions, and if any of the other if any of the organizers that have their cameras and microphones, Nitin or Dwalker, if you have any questions, please feel free to come on camera and ask your question directly. So I'm going to flip over.
Yeah, we have a question from Kenny. Do you want to get started with that, or is?
Yep. Yeah, I'll read them out. We'll start the one with Kenny. I'll read them out so that on the when we come through the video, if anybody comes in later, they'll be able to know what the question was. So from Kenny Khan from Lowe's, can you comment on reliability for components that can only be zonal? All right.
Yeah. If I kind of distract you long enough, I can pull up a different slide deck that kind of explains these things. There was a talk that I gave at SLO Conf last year. The new SLO Conf is like next week, so sign up for that. It's free. sloconf.something.org, maybe. I don't know. And the talk was called SLO Math. And I'm trying to bring that up right now. And the idea was like, if I have services that have SLOs that are not good enough for me, or that, I just can't really control, like, what can I do with them? Like, is there a way for me to aggregate them together? Like, can I get something better out of, like, the line about getting something more reliable out of something less reliable? How does that even work? And let me present this. Right. So this is tab slow math. So this is and I can show you guys the link to the talk later. The idea with this is, I should probably make it bigger. You have like two ways of thinking about composing your services. One is serially. So like A has to talk to B, has to talk to C, has to talk to D in order for them all to work. If they all have a certain SLO, in this case 3 nines, you have to ask yourself, what is the SLO of the system? And the system here has the SLO of 3 nines raised to the power of 4, right? And it turns out that's 99.6. That's not as good, right? So if you have a bunch of things that are less than 1 and you put them all together, you're going to get even less than 1. That's just how math works. Similarly, if you put them parallel, but they're still all required, it's the same thing. It doesn't make any difference. If they're not necessarily serial, but the client is calling all of them at the same time and needs all of their answers in order to like compose their response or something like that, same problem, just different shape on the diagram. So it doesn't help us at all. What if we have redundant services? What if we have 4 copies of service A, and these are now, we call these like parallel. Think about serial circuits and parallel circuits in electrical engineering. Just don't think too hard about it. Just a little bit, right? Because it doesn't actually work that way. But think about it like that. If we have these parallel services where our load balancer is able to pick one of many, and this is how load balancers work, if one of them goes down, no big deal. So it turns out that this changes the formula. So now we're going to say it's a little bit more complicated. We're going to say 1 minus the failure ratio raised to the redundancy level. So in this case, we're going to say 1 minus 0.1 times 0.1 times 0.1 times 0.1, right? So in this case, we're getting 12 nines. That's way better than before, right? Obviously, this isn't exactly correct, right? Like there's something else going on here. We don't have 12 9 systems out there in the world, and the reason why is because we have the load balancer above it, and we have the network substrate below it, and then we have other things that are going on. But if we had a perfect load balancer and a perfect network, and we had 4 independent services, and you only needed one of them to survive, you would have 12 nines, 12.6 nines. So the question that Tommy had was, how do we get reliability out of things that are only zonal? What you do is you put many of them all together, many zones, and you put a load balancer in front of them, right? So now you can get a higher level of reliability out of a lower level component. I hope that answers Tommy's question. So like a good example of this is we have VMs. You can put 1 VM in each zone and put a load balancer in front of it, and you're gonna like that layout is gonna be way better than having 4 VMs in one zone.
Mm-hmm. And that one load balancer, that's just a logical concept, right?
Right.
It's
so in Google,
all those zones?
Yeah, in GCLB Google load balancers, it's not a single VM that is being your load balancer. Like it's not a physical machine, like one machine that is yours, or even a slice of one machine. Basically, your configuration gets copied into gazillions of machines. These are called GFEs, Google front ends, and they are absolutely everywhere. And so those machines are part of a very large system, and you're basically getting a stanza of configuration for you inserted into this very large system. So this is the same system that fronts google.com, Gmail, YouTube, everything. So we take it very seriously. Like it is, in a way, you can get scared of it and say like, oh, it's a global failure domain.
Yeah.
But like, when was the last time everything at Google went down? We take that very seriously. Like, there's actually many failure domains. There isn't just one global failure domain, but it is logically one global system to the developer. So that's the caveat. Yeah.
Okay. Yeah. So even though on and you have to check it out on each cloud provider, or each wherever you're at, whether physical data center or other clouds, you just have to dig into how that provider is providing that thing that you have.
Think about an F5. Like an F5 is a box, right? It lives in a place when it has a plug, and it has many Ethernet cords coming out of it. But like a global load balancer isn't an F5. Like it isn't a single thing. It is many things. It's a little weird. So like once you have that level of understanding about all the components, you can reason a lot better about the whole system.
All right. Kenny, ask a follow-up question if that didn't catch you up. I like the one slide that you had kind of towards the end, kind of as you're building up a system. The red line, don't put your most important thing on your platform before the platform is ready. Any interesting stories about what are the repercussions or what are the consequences of adopting prematurely with something that's really important?
Yeah, I mean, I'll say when I was at not Google, we did this, right? It was a mistake, and it was a classic example of we're building this great new platform, we're modernizing the thing, it's going to be awesome, and then to be blunt, like clueless executives are like, great, we're going to use that for the new thing that hasn't launched yet and is going to change the company, and we're like, wait, no, don't do that. Right? So it's really important to get that understanding through early, and to not like provide that lure, because it is highly alluring, right? Like this thing is shiny and great, then let's put all of our eggs into this basket. And you're like, no, please. It's a bad idea. So this is my attempt to kind of like explain that. So one example of this is simply like, if you don't have like logging in place to the point where you can adequately debug an outage, it's not a big deal if it's like the who am I service or something like that. Because like if it goes down, like who cares, right? But if it's the billing service, like we're gonna have to figure out what happened and we're blind about it, or like if our new platform has a new observability suite that we don't have much practice with, like even if it's already there but we're just not very good at it yet, like give yourself time to get practice on that observability suite over time and develop some muscle memory and things like that before you put the credit card payment authorization service on it or whatever. So not that that was the thing we did.
No, we wouldn't. Even if it was, we wouldn't tell anybody.
That's right.
All right. So on the I like that you took the R9Y. You call it Ronnie as a nickname. I haven't heard that one before. It is.
Yeah, I know it's confusing.
It is interesting,
silly, and that's how you remember it.
Interesting. But on I've taken a look at that. The demo page, the r9y.dev, and it looks like it's more than just technology pieces. I know we looked at VMs and load balancer. It looks like it has some more things besides just the technology part. Mm-hmm. Can you highlight or talk about some of the other things that are important in order to have a not just a system that's reliable for right now, but a culture or something that needs to go along with it?
Yeah, the way to think about this, and this is just, it's publicly available, so anyone can click on it and play with it. The only suggestion I have is if you start out and it looks like this, and it's like this weird 3D isometric view, just zoom out once, and then it'll make a little more sense.
It goes and flattens it out. Okay.
Yeah, it goes into flat mode. So the way that it's organized is the columns are nines, right? They're like levels of availability. So we have like what we call demo, which is like 2 nines, which is I might shut my laptop and it's down, right? There's sorry, that's 1 9, 90%. Single 9, no good. Do not build a business on a laptop. We have 2 nines, which we call deterministic. And it's sort of like it has to work only this way, and we can't really do much about it. And like if we change one little thing, it's all going to break, right? And so this way we're going to have like many minutes of downtime potentially every day, right? Mm-hmm. We have the next level is reactive. So 3 nines. This is where most of the internet is. And so this is like when it breaks, we get a thing saying it's broken. We think it's this thing, and someone goes in, like a human goes in and goes like, oh, remediation steps. I think it's fix it, And this is 3 nines. So this is the 40 minutes a month stage. The next one is proactive. So this is like we've thought about it. We have a plan. When the thing breaks, like we will even have like a script ready that will just automatically fire and do the remediation for us. Most people think they're here and they're not, right? like they say, oh yeah, we have 4 nines. Then we like ask them some questions and we like look at some reports and we're like, well, we try to be 4 nines. I'm like, okay, well, or they'll say like we're 4 nines except for like those big outages that we don't count. And we're like, come on. Right. So that happens a lot. And so the other thing to think about, and then there's 5 nines at the end, but we won't get into that. The other thing to think about is the kind of the rows here. So each color in this case is like a team. So think of it as like a swim lane. So at the top is development. So there's like the software engineers who are building the product itself. We have the infrastructure level. So these are infrastructure teams generally, like they might be your traditional on-prem management team. We have the operations team, which might be separate from that. It might be the same crew. It might not. So who's actually like running the the scripts and in the NOC or whatever. We broke out observability into its own swim lane as well, because often that's its own at least area of expertise. And then the last one is people. So this is kind of culture and like planning among your team. It's like hiring. And it turns out like this whole thing is a socio-technical system, right? It's not just a computer system. It's humans running computer systems, right? And those humans, if treated poorly, can screw up the thing either on purpose or not on purpose, right? So it's important to make sure that they're like, incentivized and aligned and rewarded and all those fancy things. So
yep, right. I wish I remember the source of this anecdote, and it's not technology, but the phrase that you said, that's it's the human system, and if you treat those humans are in the system, and if you treat those humans poorly, they could do certain things. And And I can't remember if it was a Jonathan McWhorter book or Malcolm Gladwell book, but it was about a factory where I think they were making plywood or doing something with wood, and management somehow was making not treating the workers well, so they would just take the finished product that they spent how much time making this this nice product and just throw it in the wood chipper, like no. Yeah, your output, we made it, but you're not getting any of the output. Kind of a
Yep.
sabotage type of a thing.
Turns out that's real. Yep, people do that.
Yeah, so
Only digitally.
yeah, only digitally, and it may not be. I guess sometimes it's completely obvious that something's wrong, but not how it happened.
Yep.
All right, no, thanks for that, Steve. We do have more questions, a couple in the Q&A. One from Chandan. What about putting high risk first, but way lower traffic as AB? That way, all the different ways one could go wrong. So put high risk first on, but way lower traffic.
Well, then you're not really putting it on it. Like you're putting part of it on it. Sure. I think like you could test with it. I'm just saying like don't migrate the entire service and rely entirely on the new untested platform.
Yep.
If you want to test the platform by like doing some A/B testing, go right ahead. But recognize that the B or whatever it is that is on the new platform will fail. Right? There will be bad things that will happen to it on an untested platform. So just as long as you're cool with that, go right ahead. But just don't put all the eggs actually in the untested basket.
All right. All right, DeWalker, I see your camera's on, your mic's on. Do you have a question?
No, I just wanted to say hello, Steve.
Hey, DeWalker, how's it going?
Sorry. I'm sorry I had to join late. Apologies.
No, it's okay. It's okay. Yeah, so if you have a question, you can you stay on. If not, you can mute your mic and it'll
Sure.
knock down any background noise that might be there.
Got it.
All right, one question from Diva. If resources are in different zones, are isolated from physical infrastructure, and if budget is a constraint, can we rely on zonal redundancy for reliability? So it's
I think
region. I guess it's in a region. There's multiple zones.
Yep.
And the physical infrastructure is isolated in those zones. Take it away, Steve.
The question is like, aren't we defended against things failing in different zones? Like, aren't they physically disparate from? Like, it's a good intention of the question, but the point is, look at the SLO for a zonal resource, for a zonal product or service, and it's not 100%, still not 100%, right?
Yeah.
And it is still the same. Like if you have many resources in one zone, if it's entirely possible that they all come down together of a blast radius or a failure domain, right? So like a zone is a failure domain for a VM, for example, or for a persistent disk. So many persistent disks in the same zone can fail together. So so when you ask the question like, can we rely on zonal redundancy for reliability? Yes, for some reliability. So the question is, how much reliability do you want? Because if this is just like a test service or something like that, like you don't need that much reliability. And like what you're getting out of like the cloud platform is probably way more than you really need, but it is like sort of the vanilla flavor one, right? It's just what you get as a baseline. Mm-hmm. If you're putting like your most important system on top of it, you need to be like resilient to all kinds of problems. Then even the fact that it's physically isolated from different zones isn't going to help you, because there's still that 0.5% planned downtime. And sorry, not even planned downtime. We call it an error budget. But the point of it is that it's a combination of planned and unplanned downtime. So if we don't have any unplanned events, that 30-day window or whatever, we're going to use the rest of that to do something. So you have to do repairs in data centers. Like we have to like upgrade the bus ducting, and we have to upgrade the thing, and I don't know, sweep under the computers. I don't know what you do in data centers, but like there are things that we have to do, and we have to turn parts of the data center off. And if we have room in the air budget, we're just going to do it. And so you can't really just expect it to work. You have to look at the number and say like, I am going to get that level of reliability this quarter or this month or whatever.
And I think that reminds me of one of the, the air budget that's there, that you guys are going to find a way to use it. I think there's some public anecdote in the SRE books about some storage system that was literally performing too well. It was too reliable, and people were depending on that reliability. Can you?
Yeah, that's Global Chubby. So Global Chubby is a distributed lock service, and the intent is if you want to set a lock, like think of it like a mutex in a distributed system, you want to say like, yo, I am the leader of this quorum or something like that. And you want to have that in a global context so it can run from multiple, can be checked or set from many places in the world. That's a really useful thing to have. It turned out what people did was it was so useful, and it's actually a really, I don't want to say it's a really simple service to run, but they made it really reliable. Right. To the point where people were like having hard dependency on Global Chubby working all the time. And as soon as Global Chubby went down, it had all of these cascading effects that were unexpected because Global Chubby never goes down, man. It's so great. And so what they had to do was they had to say like, look, Global Chubby now has an SLA of 5 nines or whatever it is, 4 nines. I don't remember what the number was. And if we're doing better than that, we're just going to take downtime. Like we're just going to turn it off for like 2 minutes at a time, right? And they did it in a very controlled way where they're like, they would do it for 30 seconds or something like that, and people would freak out, and they would do it for 30 seconds for some people, but not for other people. Like you could whitelist yourself or allow list yourself to like be not a part of this outage because you knew you had this hard dependency. And it took a while, but we got to the point now where it's just like, nobody has this global dependency anymore, or this hard dependency on this global system anymore, which is great. But it made for a good story, so that's why it's in the book.
Yeah, no, it's a good story, and it's kind of just a reinforcement, for people that are working in technology, just to build your systems, your software part that you can control. To be able to handle failures like that. Don't depend on something always being there, because you'll end up being disappointed the time that it does disappear.
There's one more thing I can pitch while I'm here. Can I do chat? Yes. There's a new, I don't know if I can call it a book. It's a small book. It's called a report, and it's called the Enterprise Roadmap to SRE. Some of the stuff I talked about today is in this book. It's free. It's like a PDF/EPUB thing. So feel free to take it and see. Oh, I put it in the Q&A. Sorry, I should put it in the chat. Boom. I asked myself a question by accident.
Asked and answered.
There we go. Boom. Okay, so this might also be helpful if any of this like was interesting to you. We get more into like how do you do SRE in an existing enterprise context? Like what do you do in the face of ITIL, for example? And like how does this overlap with that? Or like how do we build a platform where we have many teams competing for resources and stuff like that? It's not the deepest deep dive because it's only 50 pages long, but it will give you a start. So go ahead, check it out. At me on the Twitters when you have questions, and I'll be happy to answer it.
All right, seeing no questions in the queue or in the chats. I do have one question. I can't remember if I asked you the last time you're on. But I do like to ask at least one non-technical question, and it's more a kind of a career advice type thing. So if you, the question is, what advice would you give your younger self at the start of your career? So if you go back in time, give yourself some advice, what would that be?
Yeah, that's a good question. I would say diversify in terms of experience. I think I probably spent a little too long in a few different roles. to the point where I wasn't really learning new things, and I probably got, complacent. I kind of just got good at my job and I was cool with it.
Yeah.
At the time it made sense because, I had like tiny children and stuff, and it was cool with me. I was just like, it
Yeah.
was okay to just kind of cruise a little bit, but
Yeah.
like, just pushing yourself in terms of, career growth is important. And even if it's not career growth, if it's just like moving to a different side of the company, right, is pretty cool because you can learn new stuff, and just that diversity in thought and experience creates little connections that like literally no one has had before, because no one has had your experience until you do. So it's possible that you make a connection that is like, awesome enough that you can do something new and bold and exciting because of it. And that's not going to happen if you just sort of like sit in your same desk doing, pushing the same button every day. You're not going to make any new connections that way.
No,
Was that vague enough for you?
It's vague and applies to everybody the same. No, it's a good. I don't think it wasn't that vague. But good advice. It's almost like if you think about aren't all analogies bad? If they are, this one might be bad as well. Like if you think of your information flow, the stuff you're learning as different types of water. If you're sitting in one spot for a long time, maybe it's a pond that doesn't have a lot of fresh water coming in, and gets all stagnant over time. Whereas if you're occasionally changing, maybe not changing roles all the time, you get that consistent flow. And yeah, I guess as you're doing different things, you can synthesize that information and maybe make some connections that are unique and nobody, at least nobody that has made before. Kind of that unique perspective that you can bring to solving problems or doing whatever that you're working on at the moment. All right, yeah, good advice. All right, so thank you, Steve. Thank you very much. Appreciate it.
Got it.
Little clap for Steve. Thank you very much. Appreciate your time. It's hopefully everybody's learned a little bit of something that they can take, or at least got some links if it didn't get inserted into your brain yet. You can come back and watch or flip through the presentations or click through the links. They will be posted on the event page. And what we'll do now, we'll take. I'll throw up a 5-minute break sign. But before that, just thank you, Steve. You can stick around for some virtual networking if you have time. If not, really appreciate it.
Cool. Be sure to check out the SlowConf talk coming up. The last one was slow math. This one will be slow classic literature, just as a teaser. So,
all right, we'll check it out.
Thank you,
Steve.
All right, hey, thank you, Steve.